Uh, Hello, everyone. Thank you for joining. I don't know if some people are on YouTube also, so hello to them. Thank you, Julyan, for accepting to present. So, Julyan Arbel is a director of research at Inria Grenoble, and he is specialist of deep learning and statistics, and especially on the topic of Bayesian neural networks, which is the topic of today. So thanks again, and the stage is yours.
Thank you. Okay, so let me share that. Can you see the slide now?
Yes.
Great. So it's a pleasure to give a talk to you guys today. Indeed, I will speak about Bayesian neural networks. So the most general terminology would be Bayesian deep learning, let's say. It's kind of more general. I will try to give an overview of what this is and what the current challenges are, as well as, this is what I know the best, give a bit of insights of what I did in this field. And so, yes, I'm a researcher in Grenoble at Inria. Yeah, that's essentially it. Before actually starting, I wanted to say that David and I met, well, we studied at the same place together, but I think we never really talked together there. But we met again last summer in Tokyo. This was thanks to this common friend of us, Anthony. And actually, Anthony tragically passed away last week, so I couldn't but dedicate this modest presentation to our friend Anthony. And the other guys on the picture are my kids. And this is actually taken. This was taken in this same room as where I'm giving the talk today. I didn't realize this before. So it's a joint work with a bit more collaborators than these three, but they say that the three here are the main ones. So Maria was a PhD of us at Inria in the past. Costas was a postdoc, and Stefan is also a researcher at Inria in Grenoble. Okay, so Bayesian deep learning. To introduce it, let me start with deep learning with no Bayesian at the moment, and especially large-scale deep learning. This is what we are talking a lot about today with ChatGPT and other things like that, LLMs. So, of course, all the new massive data, new modalities of data mean that we need advanced statistical and machine learning methods in order to process them efficiently. So it cannot be denied that large-scale deep learning does this very well, and it's been especially underscored last year with Nobel Prizes in physics and in chemistry. Also more in the past with the Turing Award in 2018, awarded to Lequin, Hinton, and I'm missing the third one. But there is a but. We know there are also limitations to modern deep learning, such as the fact that those systems struggle with reliability, trustworthiness. Uncertainty is not something they are really able to provide, at least in a calibrated manner. And also those systems fail to encode prior knowledge and fail to prevent catastrophic failures. Let me now move to Bayesian methods. We are somehow at the other end of the spectrum, due to the fact that the Bayesian methods are really based on solid mathematical foundations and so on. So it's really the other end of the spectrum in the statistical direction, let's say. So it's a set of methods that are based on what we call the posterior distribution. So let me just give a bit of insight on this. So what is a posterior distribution? First, what does it do? So it summarizes prior information on unknown parameters theta, and this prior information is modeled by what we call a prior distribution. It's a probability distribution, so pi theta. And it also takes into account, of course, what the data tells us, data quality, about, and the data is encoded according to the data generating process or the sampling model or the likelihood. So a posterior distribution combines those two elements together in this way. We say that the posterior of the parameters given the data is proportional to the product. Sorry, I changed a bit notation. Product of the prior, p or pi of theta, and the likelihood. It's just as the prior distribution, it's also a probability distribution over the parameter space. And what it does, on top of combining prior and data information, it does more than what we would get with a frequentist point estimate. It gives more things. It's kind of, it provides a more comprehensive inference because it gives, predict that we can also have with a frequentist point estimate. On top of it, it offers uncertainty measures and also testing procedures, for instance, and all of these are coherent in a mathematical sense. We can derive one from the others, and the uncertainty can also be propagated along all of the modeling pipeline, so on and so forth. Okay, so we've seen what deep learning is, what Bayesian inference is. So the combination of both is what we call Bayesian deep learning. This is at the crossroads of those two paradigms. And we can hope that this approach, this Bayesian deep learning approach, can address some of the challenges deep learning faces that we listed before. So reliability, trustworthiness, offering calibrated uncertainty, encoding priors, and preventing catastrophic failures. And this can be hopefully done by mixing the Bayesian inference approach with deep learning methods. So it dates back as a field from the 90s with pioneering work by Radford Neal and David McKay on Bayesian neural networks. So I'm plotting here a simple feed-forward, fully connected neural network. And what does it mean? I will be back to this a bit later, but just to give this insight first, what does it mean to be Bayesian here? It means that we encode some prior information on the parameters of the neural network, which are, in our case, the weights of the neural network. And so let's say that I denote the weights by theta L for layer L. Then I will ask these weights to be random with some prior distribution. And then I'll try to learn the posterior distribution. Just a note that Bayesian deep learning does not only refer to Bayesian neural networks. It can include as well any probabilistic framework as soon as it has some neural networks inside. So we can think of simulation-based inference, for instance, which follow a Bayesian approach in order to learn parameters also in potentially complicated physical models and so on and so forth. Okay, still trying to motivate Bayesian deep learning with a lot of colleagues. We are a lot who signed this position paper last year at ICML conference. We argued that Bayesian methods are very critical today in the age of large-scale AI. And yeah, the motivation is, as I already said, in order to assess uncertainties, incorporate existing knowledge in, especially for safety-critical decision-making algorithms. Okay, so just a very quick illustration of this overconfident deep learning This is one of the challenges with deep learning. And I just played with ChatGPT about something I liked when I was a kid, about what is called the Mandelbrot set. That is a fractal set. Yeah, it's a fractal set in the complex plane. And it is made of all of these C points, complex C points, which are the initialization point of a series. And it's made of these points such that the series is bounded. And it has this really nice form with a big cardioid. This is this black set. And we know, well, I asked ChatGPT whether this set is has an infinite surface. Sorry, no, I asked what is the surface, and ChatGPT replied that it has an infinite surface, because I think fractal means infinite something or whatever, or complete complex dimension and whatever. But actually, this is incorrect in the sense that we don't really know. I think mathematicians don't know the surface, but they know that it is finite because it's included in a bow. So this sort of incorrect answer is, I think, what we call an hallucination of a chatbot assistant. And the main problem I see here is that the chatbot or the LLM behind the scene is not able to say that they don't know the answer to a question, which means that they essentially don't know how to encode their own uncertainty. And so yeah, Bayesian deep learning methods could do this better by encoding uncertainty, and that's the strength, for which I already said a few words. About weaknesses and challenges, so I listed here scalability for the computation of the posterior distribution. This is clearly the main point of challenge for developing models, Bayesian deep learning models, because we are facing really this big difficulty of sampling or approximating the posterior distribution over spaces of dimensions that are huge, because neural networks are made of really large number of parameters. And prior specification is also a point of challenge. Okay, Bayesian deep learning is also currently, has been applied in the past and is currently applied in a large range of critical applicative domains. So I listed here some existing works. On my side, I do works on ecology, for instance, or genomics as well. So there are fields for which clearly having some uncertainty estimation is very important, and for which the Bayesian approach to deep learning helps a lot. Great. So that was a motivating introduction. I'll now move to the different parts of the Bayesian deep learning pipeline or workflow. So I consider a neural network like this one, for which, in order to be Bayesian, the first thing to do is to come up with a prior distribution on the weights. So now the weights are denoted by these W. For every layer has their own weights, which are matrices. And so a Bayesian approach starts with placing a prior on those weights. So once we have a prior, we also have, so depending on the problem we are facing, we can do classification or regression. So that will also determine a likelihood, a model. And so combining prior and model, we are in the position of having a posterior distribution. And so the next big step is to approximate this posterior. It's never in closed form, of course. So we have several options. The first that Bayesian would think of would be to sample from the posterior. It's called sampling methods. And for this, we have what we call Markov chain Monte Carlo methods, which are based on sampling a Markov chain which has a stationary distribution that coincides with the posterior distribution. This is really difficult in the field of Bayesian neural network, again, due to the fact that the parameter space is huge, dimensionally huge. So it's difficult to visit this big space. There is a work that, well, HMC is for Hamiltonian Monte Carlo. So it's a bit more advanced than MCMC. It uses also the geometry in the sense of the posterior of the distribution. So it uses, it aims at targeting places of the parameter space that are of high probability in order to not to lose time in a sense. Monte Carlo dropout is an adaptation of the dropout technique that aims to learn an approximate posterior distribution post-hoc after obtaining frequentist estimate. And then there are also other versions of MCMC called stochastic gradient MCMC that are kind of bridging SGD, stochastic gradient descent, and MCMC. So this is a big bulk of methods, sampling methods that are usually really hard to apply as is to Bayesian neural networks. Then a big class of methods are based on the Laplace approximation. And so if you think about it, well, first, what is a Laplace approximation? It's something that replaces a distribution with the best Gaussian distribution that can be fitted to this initial target distribution. So typically for a Bayesian posterior, a posterior for a neural network like this one, we would start with estimating what is called the MAP, the maximum a posteriori, and this can be done by stochastic gradient ascent, for instance. We look for the map of the posterior. We don't necessarily get right to the map because the posterior has a lot of modes, and we probably end up in a local map, just like we would have a local minimum with an SGD, but that's okay usually. So we check for a map, and then we fit the best Gaussian distribution based on computing the Hessian at this map, the Hessian of the posterior, and then use this Hessian as the covariance matrix for the Gaussian approximation. So it seems a very crude approximation because we replace a very complex posterior by a simple Gaussian distribution. But still, it is quite expensive because computing an Hessian is something expensive, especially when the dimension is huge, because it's a matrix, so it's a squared of the dimension of the parameter space. So they are like approximations that we do on top of it. The Hessian can be block diagonal, or it can be, well, it could also be even diagonal, or it can be factorized in a sense, well, Kronecker factorized, in a sense that it is sort of block diagonal for every layer. And it's something that works, that simplifies a lot the posterior, but in the end that works. There's been work showing that it's a good approximation. And then there is what we call variational inference. It's in a sense close to Laplace approximation because we replace the posterior by some approximate posterior that belongs to what we call a variational family. And once we learn the best element in this variational family, then we replace the posterior by this best element, and then we can sample just by using the approximation that we got. In my workflow, these are the first, so this is the main challenging step, let's say. And then once we have an approximation of the posterior, well, we want to do, so this would be, let's say, training. Then we want to do prediction or something. And for this, the tool that we use is the so-called posterior predictive distribution. This is also called Bayesian model averaging because it tells us which, well, yeah, it's averaging in a Bayesian sense because it takes the distribution of the data y given x and the weights, and as you can see in this integral below, we average this with respect to the posterior distribution. P of w given d is the posterior distribution. So once we have an approximation of the posterior, this is kind of straightforward to compute and then to make predictions based on this. So most of what I contributed to the field is about step one. I have been interested on studying priors. When we place a prior on the weights, what is the impact on the neural network? I'll talk about this later. But yeah, the main challenge, as I said, is on this point two. And I have one slide about it. I already actually talked a lot about it. I should have moved here, but whatever. Just to say again that this would be a very simplified representation of a posterior distribution because it's just in 1D, while we are actually speaking about things that happen in dimension that are of millions or even more. A Laplace approximation, so here the posterior is represented by the bold black line, so it would be multimodal and so on and so forth. A Laplace approximation looks for the map, which is like on the left, and puts a Gaussian on top of this map. A variational approach specifies a variational family and looks for the best element in this variational family. So as you can see here, it provides a kind of a different estimation for the, well, approximation of the posterior. And then MCMC, so sampling methods would rely on sampling a lot of points based on a Markov chain, and then approximating the posterior distribution by an empirical average of all of these points. So that would be all those orange stars. And finally, something I didn't speak about are called ensemble methods that consist in taking a lot of stochastic gradient descents in order to obtain a lot of optima of the loss function, and then to make a number of neural networks based on these, and to do predictions based on these as ensembles. And finally, also something to mention is that Bayesian neural networks could be also only partially stochastic, meaning that only a few of the units of the network, a few of the neurons could be random, while fixing a lot of the others to SGD, optima, stuff like that. So we can think of a lot of combinations. Okay, so this is it for the workflow. Let me now dive into some personal work on priors. So the main question I will tackle now is if I place a prior distribution here at the bottom level of the picture on the weights, so now the weights are denoted by W, what is the implication in terms of distributions, prior distributions, on what I call the units? So there are here those hidden units of the network at layer 1, layer 2, and last layer, for instance. And I could also ask what is the prior at the output. That's also something that holds. So it was addressed. That question was addressed from the very start of the study of Bayesian neural networks, as I will say in a minute. And then we did some work on it with Maria. And this last part of work we did, I won't speak about it. So this guy is called Radford Neal. So I like to put his picture just because he's a sort of a god for the Bayesian community. He did works in a very large array of fields, including computations. So as I said, Markov chain samplings for Bayesian nonparametrics based on Dirichlet process mixtures. He also did works on computation. So he really brought Hamiltonian Monte Carlo to the Bayesian community, I would say. He worked on the slice sampling. So a lot of computations, but the last point I want to mention, he was the first one to apply the Bayesian methodology to neural networks. And a sort of seminal contribution he made to the field, so on top of actually bringing the Bayesian approach to neural networks, he also obtained a really nice, a really fine theoretical result that I'm going to present now. So take a one hidden layer neural network, think that we are back to the 90s, so no deep learning at this time, or just because it was already hard to fit one hidden layer neural network at that time. Take such a network, place a Gaussian prior for all of the weights. So here the hidden weights of the single layer on the left of the hidden units in green, but also you have weights at the right of the hidden units. You take them Gaussian, centered, and Neal showed that when the width tends to infinity, so I denote it here by h, it's the number of hidden units, then the output converges to a so-called Gaussian process. So it's a generalization of the Gaussian distribution to stochastic processes. So a neural network, a Bayesian neural network, behaves as a Gaussian process when we have a lot of networks, a lot of units in the network, when it is very wide. So I have the set of equations that allow to prove this, that allow us to prove this. It's essentially based on the law of large numbers, because as you see, there are more and more stuff that pile up together. There is a sum, there is a zero mean. We have to rescale the variance of the prior as 1 over h, 1 over the number of units. But in the end, if we do this, all goes well together. There is a law of large number, which tells us that there is a convergence. And then the central limit theorem tells us that this is the limiting distribution is a Gaussian. Only quite recently, well, now 7 years back, this Neal result from the 90s was generalized to deep neural networks, meaning networks with more than one hidden layer. And that's nice. But the sort of limitation to this is that we have this Gaussian process in the limit, but with this result to hold requires the number of hidden units to be much larger when we have a lot of layers. When this is what we see here, the plot is showing the difference between the actual distribution of the neural network and the limiting Gaussian process. And we see that the curves are going to the right when we add more hidden layers. So on top of this, such a Gaussian process limit is used actually in a lot of works in deep learning. For instance, what is called the neural tangent kernel. It's describing the learning dynamics of neural networks. Also in something that is called the edge of chaos, that tells us how to initialize a neural network in terms of the variance of the weights on the x-axis and the variance of the bias on the y-axis. And we see that there is only a sort of a line that is called the edge of chaos here between the chaotic phase and the ordered phase. And this work as well uses the Gaussian process distribution, although it is just a limiting distribution. You know, it's only something you get in theory when you have a very wide neural network. And so this motivated some work with our PhD student, Maria, in order to actually understand what happens when the width does not go to infinity, but is kept fixed. Okay, so that's what I will present now, trying to see what is the actual distribution. It won't be Gaussian, it won't have the law of large numbers and the central limit theorem. So the question is what it is. And the description we were able to do for this distribution for the units when the width is kept fixed required us to define distributional properties. So I'm going to define them now. The first one is called the subvariable distribution, and the second one is a generalized variable tail. I'll come back to it later. And so this is a representation of so-called subvariable distributions. So this is the survival function of those distributions. Maybe not super visible here, but we can see that when the parameter is very small, the tails of the distribution are very thin, like the blue one, theta equals 1, the tails are thin, and they get larger when the parameter gets larger. And the red one has very heavy tails, because here the survival function has a really low decay. And mathematically speaking, there is a characterization of these distributions, these subvariable distributions. It's really related to what is called sub-Gaussian distributions. And sub-Gaussian distributions have tails that are lighter than Gaussian distributions, and this is the same here. They have tails lighter than variable distributions, and so it can be characterized by at least those four equivalent properties. So the first one is the most intuitive one, that says that the tails of subvariable distribution X are lighter than the ones of a variable distribution, and that's what's written here. This probability that absolute value of X goes above small x is bounded above by that exponential, and this is exactly the tails of a variable distribution with tail parameter theta. Another way to characterize this property is through the moments of X. Those normalized moments of order k don't grow faster than some constant time times k to the power theta. And then there are characterizations with the moment generating function of these variables for the last two characterizations. Okay, so here the proof of our result relies on characterization 2 in terms of the moments. In order to prove what we have, we use the fact that the moments have this upper bound. In order to get the result I will present in next slide, I need those two assumptions. So I need some prior on the weights. Here I used an IID prior and an independent and identically distributed Gaussian prior for every single weight in the neural network. This could be actually much more general, but this is to simplify things. And the second assumption is on what is called the nonlinearity, or the activation function of the neural network. And it has to be of this ReLU type. ReLU would be just the plus function, while a ReLU type, as we can see, is a sort of plus function, but that can be somehow affine. So with those two assumptions, I'm able to state a theorem that says that conditional on some inputs, so you take any image, you fix the image, x, this is a bold x, and you look at what is the marginal prior distribution for any unit, any neuron in the network, UL, and L means that I'm at layer with number L, then it's going to be subvariable with a tail parameter that we described in the previous slide, that is exactly L over 2. So it's a subvariable L over 2, and the nice thing is here that this L over 2 is optimal. We cannot, so subvariable is only an upper bound, but we cannot improve on this L over 2. Okay, so we are kind of far from the Gaussian result of Neal that we presented before, just because we are considering a fixed network, fixed widths. And so with numbers, this gives the following things for the first few layers. The first layer with L equals to 1 is going to be subvariable 1 over 2. And subvariable 1 over 2 is just sub-Gaussian, because in the characterization, the parameter that comes up is a 1 over theta. So here it makes a square inside the exponential. So it's exactly just like the Gaussian. So this was a known result, right? That the first unit are distributed as Gaussian. But then in the second layer, we get something that is subvariable 1. So that means sub-exponential, and so on and so forth. So the deeper we go inside the depths of the network, inside the network, the more heavy are the tails of the units. We generalize this to, well, it's not really that we generalize, but we prove a finer result in order to have not only an upper bound, but also a lower bound. You can see in the definition of a generalized variable tail that we have not only the upper bound for the survival function, but also the lower bound. So let me come to a more precise definition. We now have a parameter beta for the generalized variable tail. It's also a tail parameter. And we say that we are a generalized variable tail if the survival function, f bar, can be upper bounded and lower bounded by quantities, exponential quantities like this. The important parameter here is the beta. This is what tells us how heavy the tails are, while the L1 and L2 functions are simply what we call slowly varying functions. And those functions are, well, we should think of them as either constants or log functions or functions that essentially stay, well, converge to a constant or stuff like that. So they do not really count in the description of the tails of the distribution. And so in order to prove a result based on this characterization of the distribution, we had to prove a few properties of these families of distributions. So they are stable by multiplication by a constant. The product of independent random variables within this family remains in the same generalizable tail family, but with an updated parameter, like here. And then the sum of variables remains also in the family, but with some condition on their dependence. If they are independent, then we can send them and that's fine. But if there is some dependence, we have to pay attention that the dependence is not too strong in the negative direction. The thing that we want to avoid is that we sum x and minus x. So you do x minus x, you just kill everything and go to a constant, a Dirac mass at 0. And this is something you want to avoid because a Dirac mass has no more tails, right? It's a Dirac mass. So the dependence condition we have at the very bottom of the slide helps us ensure that the sum of random variables remains a generalizable tail. And so we were able to prove that the units of a neural network, of a Bayesian neural network, are generalizable tail, just like before, based on the fact that we were able to prove that those units satisfy the dependence condition below here. And so that's a streamlined, a finer result than the solvable one because it gives upper and lower bounds. And as made explicit here, that holds for any prior distribution that is within this family. So not only Gaussian distributed as I stated before. Okay, so I think So an interpretation, this is probably my last sort of technical slide. This is in order to get an intuition of what's going on with our results. So I talked a lot about these distribution properties of the priors and so on. So what did we prove in the end? So we start with a weight distribution. Let's think it Gaussian. That is, as written on the top left, as exponential minus w squared. That would be same prior for every weight. Then what we get is that for the units, the prior distribution is actually transforming into something that is sub-Gaussian or generalizable tail, or it's sub-Weibull, sorry. And so that's more like what I have here in red as exponential minus u to some power 2 over L. And so taken together, when we have a prior distribution that is more and more heavy, it's like having a penalty that is more and more concave. It's imposing a penalty on the training algorithm that is more and more concave. And so the intuition we have behind this is that it makes parameters more, it induces some sparsity in the parameters, because the penalty that is concave tends to sparsify the parameters, like what we would have at the deeper layers, as we can see on the plots, is something with those pikes, and that induces sparsity. Okay, so I've put here the 2 papers that did those two definitions of sub-Weibull and generalizable tail distributions. A final point I wanted to somehow advertise is a review paper on Bayesian neural networks that we wrote with colleagues. And yes, that's essentially it. Just to wrap up things. So I spoke on prior distributions mostly, because this is the sort of results I got, but I also spent some time at the beginning on those this second point of the Bayesian neural network workflow, where this is actually where most of the challenges, the practical challenges of actually implementing stuff exist. I could provide pointers to actual Python libraries that do implement Laplace approximation, for instance, or other directions. And so just to conclude, the main motivation was to study the distribution of the units rather than the distribution on the weights. This is an interesting way to look at the problem because the units are something that are more interpretable than the weights. It's difficult to say I want a prior like this for the weights, while at the output of the network, for instance, if I know that the prior distribution does something, it's more interpretable. There are a lot of capabilities for Bayesian deep learning to enhance AI, let's say, and deep learning. And so the important challenges I see from my point of view, I like to be able to not only characterize the prior distribution, but also the posterior distribution. I didn't really talk about distributional properties of the posterior, so it is current work with some colleagues. And the second point is when we use approximate posteriors, we sort of lose the traditional Bayesian updating rule. And so a question is, what's actually what I mean by UQ is uncertainty quantification. What actually is the uncertainty quantification provided by an approximate posterior? So there is a lot of work on this, but it's something that is not always straightforward to interpret. And of course, the scalability to large models is an important question now. That's mainly it. Thanks for your interest, and here are some references. So I will stop sharing in order to be able to see you guys. Yes.
Okay, thank you very much, Julyan. Very nice talk. We'll take some questions. Do we have time for questions, Julyan? I know you have some obligations.
Yeah, it's fine for me for more than 20 minutes in case. I mean.
Okay, great. So first, a question I had is when you study the prior distribution of the unit, well, you study the distribution of the unit based on that the priors on the weights are Gaussian.
Yeah.
But in Bayesian neural networks, do the weights keep being Gaussian along the training, or is it just at the initial training step that you get Gaussian weights?
Yes, that's only at the initialization. Let's say it's
but so
yeah.
So that would be for any Gaussian initialization is common in neural networks, whether Bayesian or not, no?
True, yes. It's also very common, yeah. Like the Hay initialization or Gloro and yeah.
So yes, so it seems your results are quite general beyond Bayesian neural networks. It applies to all.
For initialization, it's true that we like to somehow sell our work in the sense that it also applies to, so we derive it in the Bayesian setup for prior and so on, but also for initialization, it's something that has implications.
Yes.
Because, yes, it's a way to, yeah, initialization is something that is really researched a lot because bad initialization makes learning impossible mostly. So there are a lot of stuff around it. And yeah, it's true that the part of the work can be also can find applications in this. I thank you for bringing this point that I forgot to say.
Okay,
Yeah.
and then I was wondering whether, because you presented results mostly on multi-layer perceptron architecture, but does it also translate to different architecture, convolutional transformers?
Yeah.
Or
Yeah, the convolutional is the easiest I can think of. In the paper, we have also a result that says that since the convolution is also something linear, everything works well for convolutions. It's true that we never really thought about transformers, for instance. It would be, I don't know. And for RNN, I don't remember. I think RNN makes it more complicated with the recurrent loops. But for sure, convolutional, it's essentially the same stuff. And then transformers, I have to think about what transformers are more deeply.
Okay.
Yeah, but good question. Yes. Yeah.
And then you mentioned the library on Laplace approximation. I was wondering if Bayesian neural network can be implemented in standard frameworks like TensorFlow or PyTorch.
Yes. Do I have the? Yeah, sorry, I had slides. I couldn't add it on time to. So it's how is it called? Laplace torch. So yeah, it's based on PyTorch.
Okay.
And so I'm not a contributor of this, but close colleagues are, and they usually sell it in these lines. Like you have a pipeline, and you just essentially add one line, or if crossing fingers, but you can really in a light way just add this Laplace stuff, and then get some Bayesian interpretation to your training, and also Bayesian some of the advantages of being Bayesian. And I think it's really light. So I will share this to you, and then you can also share to others.
Okay, thank you. And also, last question for me. You mentioned you work on applications in ecology. Can you give a hint of what are the uses of Bayesian neural networks in ecology?
Yeah. So yeah, nice. In the past, I did Bayesian modeling of. So it was not deep learning. In what I was mentioning is current work. So let me speak first about what I did in the past. It was modeling of the distribution of species in a field, for instance, in a mountain or whatever. You have measurements at sites, and you have covariates with it, like altitude and weather and a lot of stuff. And the idea is to model how the species are distributed in the land, also with what is the impact of the covariates, with the aim of understanding how they interact. So it's called joint species distribution models, in the sense that we don't learn one species separately, but all species together. And the Bayesian approach here makes it possible to do some dimension reduction in the learning of the interactions between the species, because if we have a lot of species, then their interaction is a square of their number, and so we need some dimension reduction. And so being Bayesian was helping here, but it was not Bayesian deep learning, it was just Bayesian inference. And more recently, we hired a postdoc who uses some neural networks in order to learn some complicated function on the relating what is it called? I'm a bit lost now, but in order, sort of doing complicated regression. And in the past, the ecologists haven't really used neural networks in order to model those things. So adding a neural network at this point in order to learn some dependence is supposed to help. So this is ongoing work for which we will do neural networks, but also from the Bayesian approach in order to also get the uncertainty quantification. So nothing really pas très abouti, only ongoing, let's say.
Okay, thank you. Are there any other questions in the audience? I don't see any hands raised.
Yeah, I didn't ask you, David, what are the current lines of research and interest. So maybe I could have focused a bit more on some specific stuff. It was kind of technical, so I hope it was, it was okay.
No, I think it was a discovery for many of us. So you did great.
By the way, I will provide the slides in case some of you guys want to be back to it.
Thank you. And don't hesitate if you happen to pass by Paris, come and visit us.
Yeah. I will at some point in early July, so I will contact you.
Okay, let's keep in touch.
Yeah.
Okay. See you.
Thank you for the nice invitation. Have a good day.
Have a good day. Goodbye.
Bye-bye.
Thank you.